So hi everyone, thanks for coming. Today we have Cliff Liu from Princeton University as our speaker. He's going to talk about his work of sublinear time algorithms for graph problems. Let's welcome Cliff.
Thank you. Hi everyone, I'm Cliff. I'm a fourth year PhD student in Princeton University, and I think I will be joining your group in next semester as a postdoc after I graduate. Today, I'm happy to be here in this seminar to talk about my recent research. So the topic is sublinear time algorithms for graph problems. And let's begin with some introduction. So graph problems. So graphs from real-world applications are growing super large. So imagine a front graph of social network from Facebook. But this graph is too large to process, right? So like the best you can do in classic algorithms is like linear time, but the linear time is usually not fast enough for these big data applications. On the other hand, computational resources is relatively cheap, like the number of CPUs or remote memory. And so that's why we will be considering two models to get something like sublinear time algorithms for these problems. The first one is called parallel computations. And the second, we will be considering the streaming model. And we consider these two models mainly because the recent success of like Hadoop, Spark, these conventional platforms has achieved great success. I will introduce the theoretical models first. So for the streaming or semi-streaming for graphs, usually we will consider the edges of the graph is reviewed one by one in adversarial order, and this is the most popular case. But sometimes we will also consider the edges arrived in a uniform random order. A slightly stronger model is like you can also consider that the vertex of the graph is arrived one by one, and every time the vertex is arrived, all of its incident edges are reviewed at that step. And in the semi-streaming model, we are allowed to only use n times polynomial space, and the goal is to minimize the number of passes of scanning the string. And we also are interested in the space usage and sometimes the work, which is the total number of primitive computations. So, and in the parallel computational models, we will introduce two major models. The first one is called the massively parallel computation model, the MPC model. And the second is the classic parallel random access machines, the PRAM model. And we will talk about this in details in the next slide. So for the MPC model, the input is like m plus n words, and it's distributed into many machines. And each machine only holds a polynomial fraction of the input. It's not all, it's just something like big N to the delta, and the delta is some constant. And the computation proceeds in rounds. In each round, a processor can send or receive the number of maximum of its memory size words in a round. So this is called a communication round. And but the computation round, you can basically do anything in a single machine, but you cannot send anything. You can even compute. And usually it does not compute some like NP complete problems, but we consider it to be free. And the goal is to minimize the number of communication rounds. The classic PRAM model is a little bit different, but it has a more intimate relationship to circles and the complexity theory. So you have an unlimited shared memory, and each processor only holds constant words. Each processor can read or write a cell in the shared memory in constant time but usually there is a trade-off between the time of computation and the number of processors. So your goal is to minimize the time, work, or the processor number. So the work is defined, it can be upper bounded by the product of the time and the processor's number. In the family of PRAM, there are actually many variants. The weakest model is called exclusively read, exclusively write PRAM, and it does not allow concurrent read or write from multiple processors to the same cell in one time step. And the slightly stronger model is concurrent read, exclusive write, if you allow concurrent read to the same cell at the same time. Usually, the most popular model in this family is called arbitrary CRCW, is you allow concurrent read or concurrent write to the same cell. But if concurrent write happens to the same cell in the same time, an arbitrary processor wins the write, which means your algorithm need to be correct and has the claimed time bound no matter which processor wins the write in any step. But there is also a stronger model in this family. Like if you consider the priority CRCW is like when multiple processors write to the same cell, the processor with the highest priority always wins the write. And in this talk, we'll be focusing on the arbitrary CRCW model. So the outline of the day's talk is like we have talked about the motivations of the models, and then I will talk about the parallel connectivity algorithms, and I will introduce the problems later. But for this part, we have two results. The first result is a very simple algorithm with a state-of-the-art log n running time, where n is the number of vertices in the graph. And this algorithm, there are actually many algorithms, but we will introduce one. It's very simple. It's like 5 or 6, 7 lines of code. And then we will introduce a more complicated algorithm, but the running time beats log n when the graph diameter is small, which is the first PRAM algorithm to break log n, and is on the arbitrary CRCW PRAM. After this, I will introduce matching algorithms on streaming model. The first result is a 1 minus epsilon approximate algorithm for bipartite maximum cardinality matching, and the number of passes is epsilon to the minus 2. And then I will introduce the algorithm for maximal weight matching in bipartite graph, and it requires square root m passes. All the previous algorithms require like n log n passes. So this breaks the n barrier when the graph is slightly is not so dense. So let me introduce the connectivity problem. So it's perhaps the most fundamental graph problem. So in the undirected graph, you want to find all the connected components. So the component is just the maximum set of vertices that is pairwise connected by a path. Like in this graph, there are 3 components, right? So the input is a graph G, where n is the number of vertices and m is the number of edges. So initially in parallel computing, each edge only knows about its 2 endpoints and nothing else. And for the output, each vertex needs to know a unique vertex in its component. So let me briefly introduce the history of this problem. So the first algorithm that achieves log n time is by Slovak and Wishkin. It uses linear number processors, m plus n, and is on an arbitrary CRCW, and the algorithm is deterministic. And later, this algorithm is simplified. And but you can see that the number of processors is linear. So times them together, the work is actually m plus n times log n, which is not optimal, because the optimal is at least the sequential time, right? Is like linear. So they made the improvement of this algorithm. It's actually a new algorithm, but they have the number of processors that has an inverse argument function here. So if you times together, you still has an inverse argument factor overhead comparing to linear work. So this algorithm also has a simpler version. I think it uses Spender graph, and yeah, but it's not linear work. But as you can see, log n is something like you cannot break. I will talk about lower bound later. Then there's actually a much simpler algorithm by Gazit that achieves linear work, but it's a randomized algorithm. So this time bound hold with high probability. If you use a much weaker model, like the weakest, the exclusively read, exclusively write model, then it actually the problem becomes much challenging. So this algorithm by Chong and Lam, it has log n time. It's deterministic, but it uses linear number of processes. But actually, there's an optimal algorithm which is randomized that achieves linear work and log n time. This algorithm is super complicated. Our result in like 2019 is a super simple algorithm that works in the MPC model or in the combining CRCW model. I would just say MPC model because I'm not going to introduce new things. So the running time is state of the art. The number of processors is like linear, but this algorithm is very simple. It's comparing to all the previous works. If the graph is actually, so the diameter of the graph is just the length of the longest, the shortest path among all the shortest passes. So Adoni et al. Has a breakthrough, I think it's Fox 18. They have a new algorithm that runs in log diameter times log n time. So this algorithm works only on the MPC model and is randomized. And later this algorithm is improved. So this multiplicative factor is improved to additive factor, log D plus log n time. And still only works on the MPC and is randomized. So our result is just, well, it's the first PRAM algorithm that breaks the log n if the diameter is not so large. And it achieves the same running time as this algorithm. But the model is much weaker. It's arbitrary CRC. I'll talk about the model difference later. So note that if the graph is slightly denser, like M is n to the 1.1, so n is the number of vertices, m is the edges, then actually our algorithm runs in log d time with high probability because the second term becomes the constant. So this is conditional optimal based on the two-cycle conjecture. So in most cases, MPC model is actually much powerful than a PRAM. For example, if you want to compute the all function of MPs, you actually require log n time on a concurrent read exclusively write PRAM. So which implies connectivity or connected components requires log n time on a CREW PRAM. Also, prefix and sorting are mostly used as a primitive in most algorithms. It requires log n over log n time on a priority CRCW PRAM. It's a very strong PRAM with any polynomial number of processes. However, these two problems can actually be solved on the MPC in constant time because there is some constant specifying the memory of each machine. So, however, in these two algorithms that I mentioned, the log D algorithm on the MPC, they all use prefix and sorting extensively on the MPC. So it's actually some primitives and it heavily, if it is not constant time, then none of them algorithm holds. So if you, for example, how about if you want to directly simulate their algorithm on a PRAM? Well, if you simulate prefix and sorting using existing result, it actually suffers a log n over log n slow down in the running time, which means there's no improvement over log n because any of their algorithm has a log n factor there. So you cannot do a direct simulation on a PRAM for their MPC algorithm. You need new ideas. So before going into details, let's just talk about the basics in parallel computation for the connectivity algorithm. First of all is how to represent a component, where you just label all the vertices in each component with a unique vertices in the component. Because if you do so, you can test whether two vertices are in the same component by simply comparing their labels. Let's assume the n vertices are labeled by, they have ID 1 to n, and they are m edges as we talked about. So we will do minimal labeling actually. So we will label each vertex, eventually label each vertex as the minimal vertex in its component. So for example, this graph or these components, the minimal label is 8. So eventually all the vertices in this component will be labeled 8. So this larger component because the minimal vertex is I. So eventually all the vertices will be labeled 1. So this actually is effectively it gives a tree, right? Because 1 is the root and everyone point to 1 and the 1 point to itself, which means there's a loop here. So eventually we want some tree structure that is flat. Flat means that has only height 1. But during the execution of the algorithm, because the component will be growing bigger and bigger because everyone does not know or everyone else in its component yet. So during the execution of the algorithm, you might have something like now flat tree, but there are more than 2 trees but corresponding to the same component. But this is still trees, so we can define the directed graph defined by these pointer structures. So the only cycles are the loops, right? And the diagram consists, and if V is a loop, if and only if V is equal to its parents, the parent pointer. So 1 is a loop, 4 is not. And V dot P is the parent of V if V is not a loop. And we maintain the invariant that the labels never increases. So which means all the cycles must be loops. We provide 7 extremely simple algorithms on the combining CRCW PRAM or MPC. And 2 of them runs in log n square time. And we also provide a lower bound, so which means these 2 algorithms are tight. And for another 3 algorithms, 1 runs in log n square time, but we don't have a lower bound. And 2 of them runs in OD time, it's like a BFS. And another 2 of them runs in log n time. And I will introduce 1 of them with log n running time. So here is the algorithm. We call it algorithm R because it stands for loop connect. So initially we label it.
Do you mind going back to the previous slide? Yeah. I was confused because suddenly there are 7 algorithms.
Yeah. Yeah.
What's COM, C-O-M-B?
COM, C-O-M-B, sorry.
You see 7 extremely simple algorithms on COM, CRCW, PRAM.
Yes, on the model called combining CRCW PRAM. This is the new model that is effectively, it has almost the same power as an MPC. So I just call it an MPC algorithm. So
okay, so I'll just think of it as MPC basically.
Yeah, you can think of it as an MPC, but actually it is a CR concurrent read, concurrent write PRAM. But whenever multiple processors write to the same cell at the same time, you can specify a symmetric function to decide which processor wins the write. For example, with min means whenever multiple processors write to the same cell at the same time, the one writing the smaller value, the minimum value wins the write. So if there are like more than one processor write to the same cell, the one with the minimal value wins the write. So if eventually the processor which is going to write the minimal value will write the value into that cell.
But MPC doesn't allow concurrent write, right?
MPC, because it has a computational round and the communication round, so it actually can simulate the concurrent write in constant time. Because you can do a tree structure that the height is like 1 over delta.
Mm-hmm.
Because,
I see.
Yeah, because each processor holds n to the delta memory, right? And it can send that amount of messages. So you can do a tree. The number of branches of each node is n to the delta, which means you only need 1 over delta layers of the tree to broadcast the information from the root to all the vertices, to all the machines, right?
Yeah.
So this is a very usual mechanics in MPC. So most primitive computations in MPC can actually be done in 1 over delta time or round, which is a constant.
Mm-hmm.
So MPC can do many power things. So if you can do sorting, you can do indexing. If you can do prefix sum, you can do many crazy stuffs all in constant time.
Yeah, that makes sense. Huh?
Yeah. So yeah, because I did not introduce the combining CRC.PRAM, I will just call it MPC. So the algorithm pseudocode is like this. So initially, you just let each vertex do, well, you initialize the parents at itself, which create many self loops. Then you repeat the following. In each step, for each arc, VW, you do the following. If V is pair, I will illustrate this. So let's just go over it here. So if V's parent is strictly smaller than W's grandparents, and the W's parent is a root, which is this statement means, then you just update W's parents, the new parents, to V's parents. And note here, for each arc, it happens concurrently because it has a processor for each arc. So you actually using the main as a combining function, or as I said, the MPC, you just broadcast this in one of the data rounds to do, because because W's parents is many processors want to write a value to W's parents, new parents, but only the minimum one wins. This is what happens here in parallel computation. And next, still in this loop, you update with new parents to with old parents, Actually, old or new doesn't matter, but we are not going into details here. So you repeat this loop until no parent pointer changes. So this is the entire algorithm. Let's do an illustration. So this step is like for parallelly for each arc, you do the root connect. What does this mean? Is like there's an arc VW denoted by dash, and this statement says W's parent must be a root. And for this arc, you do the following. If V's parent, here old parent, is strictly smaller than W's parent, because W's parent is root, then you update W's parents, new parents to V's parents. So initially there are two separate trees like this. After the root connect step, it becomes a single tree like this. This is this root connect step. Then the second step is called shortcut. It is very obvious in many algorithms like this. So it just update with new parents to with old grandparents, because it simply halves the tree of the trees, like almost, I mean. So we claim that this algorithm runs in state of that log n time. So the high level main idea is you want to track the sum of the height of certain trees, then you will find out that it decreases by a constant factor in every constant number of runs. And this is some potential function going on. So this is some high level idea, but now I'm going into a slightly more detailed version of the proof, but it's not complicated.
And I guess what's the main difference of this algorithm and the original algorithm by Uzi Vishkin and what's the second author's name?
It's very complicated. Actually, we formalize all the previous algorithm in our paper, and so this is our algorithm, right? It's like it has about two steps in the loop. The first is a root connect, the second is shortcut. They do some crazy things like 7 steps. You need something like a root step. You need a star hook. You need a shortcut in like do it twice. Basically, it has like 20 lines of code, something like this. And the proof is like, it's very complicated.
So is your algorithm is like the asymptotics also better than the Vishkin algorithm?
You mean the theoretical bound? Or what?
Yeah.
The theoretical bound is the same. Use a linear number of processors and log n time.
I see. So you achieve the same asymptotical bound, but it's much simpler.
Yeah. It's much simpler. It's like, I don't know how to say this, but their algorithm is actually hard to understand in the first glance. You need like read their paper very carefully, but we managed to formalize all the previous algorithms into our framework. So there are pseudo codes like this in our paper for all the previous algorithms. You can see the difference. And
yeah.
So just go over some high level ideas of the proof. So the first statement we're going to prove is like after 2 rounds, all the trees contain at least 2 vertices except the singletons. And we define a tree to be passive in a round if it does not change during that round. Change means any parent does not change. Any parent or any, sorry, the parent of any vertex in this tree doesn't change. And any other vertices not in this tree does not update its parents to a vertex in this tree. Then this tree is called passive. Otherwise, it's called active. And the potential of an active tree is its height plus 1. So if the height is 2, then we define the potential of this tree to be 3. But if this tree is flat, which means has height 1, we define its potential to be 3 also. The potential of passive tree is defined to be 0, and we will need this potential function. So the idea is like you let T to be an active tree at the end of some round K, and we define the constituent tree of T at the end of some previous round J to be the trees, actually a set of trees that forms the tree T at the end of round K, because this large tree can be formed by many small trees in some previous rounds. So this is defined to be the constituent trees. And the potential of T in round J is actually a set of trees potential is the sum of the potentials of all its constituent trees. The basic lemma we are going to prove is that first of all, the potential of T never increases. Secondly, we prove that in 5 consecutive rounds, the potential of the tree decreased by a factor of at least 4 over 3. Let me highlight the difference between this and the previous algorithms is that they consider things going on in round by round consecutively, but we consider what happens in consecutive 5 rounds or even 5 or 6 rounds. But their analysis only works round by round, but our analysis works for multiple rounds. So I think I can skip this because it's just some more details of the proof. So so we have go a much simpler algorithm with log n running time, and now I'm going to talk about the log d time algorithm of the arbitrary CRCW PRAM. So the high-level idea, let's consider arbitrary paths in the graph. If each vertex contracts to a leader vertex with distance at least 2, then the path will contract to one vertex in log diameter round, because the diameter is the largest length of the shortest path among all the passes. So it's like a matrix multiplication repeatedly, right? Because the path just eventually it will point to one leader vertices in log d rounds, because it halves the distance every round. But you cannot do this naively matrix multiplication, because, well, if you do so, you might not have enough space, because a vertex can have n neighbors, and all its n neighbors can have n other neighbors, which means the leader vertex might need n square space, but it's obviously not the case because we want the linear space at most. So so the key idea in the Fox 18 paper is that, well, if every vertex has degree at least b, which is initially m over n, then you just sample each vertex as a leader independently with probability log n over b. Then after this, each vertex will has a neighbor has a neighbor which is a leader with high probability because it has degree at least b, right? You just do a channel. Then the number of vertices will reduce this to n over b with high probability because it just computes the expectation. So after this contracting to leaders in one round, now each vertex would have more space. How many spaces is just the total space over the number of leaders, which is b squared. Well, note that the budget of each vertex goes from b to b squared and to b fourth in the next round, which is double exponential progress. So the number of outer loops is actually log n. So because the second base is b, initially m over n. And each contraction is like a matrix multiplication. So it actually requires only log d time. So times together, the running time should be log d times log n. This is just some high level ideas. If you want to improve this to log d plus log n, then you actually need another idea from Fox 19. That is, instead of increasing the degree of each vertex uniformly to at least b in each round, they allow vertices to have different space budgets. So they define each vertex to have a label, initially at level 0, and a vertex at level k means it has a budget space of m over n to the 2 to the k. So the maximum level would be log n because, well, once you reach the maximum level, the budget is like n, which is enough to store everything, every possible neighbors for each vertex. So let's consider arbitrary paths here, and these are the levels. It's just simple example, like if you are at level 2, the space budget you own is m over n to the 4. They maintain the invariant that each vertex v either increases its level or the vertex at distance 2 on this path decrease their distance from v to 1. Let's consider the first vertex as v, as our v. So after each like 4 rounds, either this vertex increases its level to 3, or all the vertices at distance 2 on this path reduces their distance from v to 1, like we add a h here. Together with the property that the skipped vertices has level no more than its neighbors, they can prove a log d plus log n time bound using a potential argument. So how does this running time come from? Well, the intuition is that after log d plus log n time, you either will have something like repeated matrix multiplication like this, or the vertex reaches the maximum level because it either has a matrix multiplication step or has a level increase step. So this is just some intuition. But in the PRAM, you have many, actually the things are very different. So for example, the basic thing is like a vertex at level k has a budget space of m over n to the 2 to the k, but you have to assign processes or spaces to it. Well, what we do is like you reduce the number of vertices to n over polylog n in only log n time. Then you can use the constant time approximate compaction. Approximate compaction is like you're giving a 0, 1 array of length n, but has k ones. You compact this array to another array of length like k times 1 plus, and it's almost k, like 2k, but with high probability. So which means you remove most of the zeros from the array, which is called compaction. So this technique is actually because you compress the array to another array, which gives the indexes that can be used to assign processes. So our invariant to maintain is like if vertex v does not increase its level, then all vertices within distance so must connect to v. So the key idea here is hashing. So initially or during the execution, each vertex v owns a hash table, and all neighbors hash themselves to this table. But you will lose some neighbors, but it doesn't matter. So in the expansion step, hash these vertices in the hash tables of the vertices. In the hash table, because you want to do distance 2, because so you have 2 layers of hash tables. So after the hashing, you want to hash all the vertices within distance 2 to the hash table, to the new hash table v. So this is the expansion step. So, but if there is a collision when hashing, the key idea here is you just increase the level of v. So why? Because you want to maintain this variant. So if there is a vertex within distance 2 does not connect to v, then its level must increases. So this is when we see a collision. which can be detected. So you might lose some vertices within distance too, like I said, but like I said, we cover this case by level increase. So we carefully choose the size of the hash table such that well, the level will remain the same with good probability. And we can also prove using martingale that the total number of processes is linear. So the first stage is that after log d plus log n time, any path would contract to at the most 2 vertices because you can use the invariant improved before that the distance halves every round, and which means after this number of steps, the diameter of the graph is actually a constant, like 1 or 2, I think is 1. And this can be checked by doing another round of hashing, and you see whether any hash table changed or there's a collision. So after this point, you have a graph, which is a set of clicks, but you still don't have the components of the graph. But we can borrow an idea from the Fox 18 paper, is that every vertex obtains enough neighbors in constant time, because their algorithm proved this in log d time, but now the diameter is a constant. So in constant time, we can have progress in the budget, which also lead to double exponential. So it would terminate in log n time, which does not influence the total running time. But it still uses the hashing, but in a different way. So basically, our paper uses the hashing like several places, but it's very different. So formally, the result is like this. So there's an arbitrary CRCW PRAM algorithm that computes the connected components in log d plus log n time with this is we call it good probability because it's not always high, using linear number of processes. We also has another result that is log d times log n time with good probability, but it can compute the spanning forest. So the spanning forest is slightly different than component because you need all the component to be a tree. Note that if the graph is slightly denser, both of these algorithms runs in log diameter time with high probability, which is optimal under the 2-cycle conjunction. So the 2-cycle conjunction is that you cannot distinguish a cycle of n vertices or 2 cycles of n over 2 vertices in small o log n time on a PRAM. And it's believed to be true, but it's just a conjunction. So there are still open problems in this related to this problem. For example, can you obtain the exact log d time? You remove the additive factor if you can. And it is possible to obtain a log d plus log n time bound for spanning forest and other graph problems on PRAM or MPC. So for now, there is not even a log d plus log n time bound for spanning forest, even on the MPC. So yeah, the existing result is only for components, for connectivity, the log d plus log n time bound. And next, I will talk about matching algorithms, and it's in the streaming model. We have 2 results. The first result is a simple algorithm. It has it achieves 1 minus epsilon approximate for bipartite matching. It's actually bipartite maximum cardinality matching only, not for weighted, and in epsilon to the minus 2 passes. And after this, I will talk about the exact algorithm for bipartite matching, but it works for weighted graph, and it only requires square root m passes. And all the previous algorithm either is not in semi-streaming, or all the semi-streaming algorithm requires like the base is I think is n log n. It exists for like 40 years, but it cannot break the n. But our algorithm can break the n barrier if m is not n squared. I mean, if the graph is not super dense. So the history of approximate matching algorithms is like this. So you can achieve a 1 over 2 approximation. That is, you can compute a matching that is half the value of the maximum matching in one pass by just greedily add the edges that is not coincide with the current edges into the set. It basically computes the maximum matching, not maximum. So it can be proved to be a half approximation easily. And yeah, but the first algorithm to break the 1/2 approximate is by 2004 FKM, and the approximation ratio is like 2/3 times 1/epsilon, and the number of passes in 1/epsilon times log of 1/epsilon. The first algorithm to achieve is near optimal 1 minus epsilon approximate is by Mike Reddy 2005, but the number of passes is like super exponential. However, using the similar idea, actually in EKS 2009, they can give a polynomial in 1/epsilon passes algorithm here. All these algorithms are based on some form of augmenting passes. But if you're using tools for optimization, you can get this, actually is a totally different idea, but the results are very interesting. So for example, and Guhan 2011, I think they use multiplicative weight updates. They have an algorithm of 1/epsilon to the 7 times some log factor. And this algorithm is actually not that complicated, but they have a more complicated version later using linear programming. But they has a lot, the number of passes is much better, 1/epsilon cube times log n. And later they use a more complicated idea to give a improved passes bound is 1/epsilon square times log of 1/epsilon. But this actually this algorithm has a drawback is like the space requirement is like n over poly epsilon, which means, well, if epsilon is some very large polylog n, 1/polylog n, or I mean, when epsilon is too small, you want to achieve high accuracy, it might not work in semi-streaming because the space requirement is too high. Later, there's actually a study, a very simple actually algorithm is by, I think it's Stock 14, that the number of passes has a dependence of n, but it's much simpler. All of this works in the traditional adversarial order edge review fashion. But if you consider the stronger model, that is, like I said, the vertex arrived one by one, and every time it arrives, all of its incident edges is reviewed or are reviewed. Then Karpov has an algorithm that only requires 1 minus epsilon square passes, but the model is different, it's much stronger. So our algorithm is 1/epsilon square passes, and it's on a weaker model. So it's stronger than this result because they require vertex arrival. So let's give some basics in auction algorithms for matching, because our algorithm is based on auction, combinatorial auction. So in a bipartite graph, the left vertices are called items, the right vertices are called bidders. And when the item J is matched to bidder I is called the owner of J, or we simply say I owes J. And each item J has a price of Pj, which is initially 0, and we are capped at 1 during the algorithm. This is our simple auction algorithm for matching. So you repeat the following. So epsilon is 1 minus epsilon is the approximation factor. And you repeat the following for 2/epsilon square rounds in each round. For each bidder I with no item, I mean, if the bidder I is unmatched, then you define the demand set Di to be the set of neighbors of I with minimal price strictly smaller than 1. That is, you go over all the neighbors of I, and if the one with minimal price has a price of strictly less than 1, you add it to the demand set. After this step, it can be done in 1 or 2 passes. You consider the subgraph. that is defined by all the bidders and its demand sets. Then you just found the arbitrary maximum, not a maximum, matching M prime of this subgraph. This can be done in one pass. And given this maximal matching, you just state the new owner of J to I for each pair ij in this matching. So which effectively means the old owner of J owns nothing now. And for this item J, you update its price to be epsilon more. So you repeat these 4 steps for this number of rounds, and you just return the items with owners as our final matching. So the space and the passes are actually easy to argument. So in semi-streaming, finding an arbitrary maximum matching can be done in one pass because you just add the feasible item bidder pair to the current matching when that age is reviewed. So the passes is natural. For the space, well, storing the maximum matching in each round and the ongoing matching we are computing for output takes only n polylog n spaces. And storing all the item prices also takes O(n) spaces because actually you don't need epsilon to be super small. Epsilon should be at least 1 over n plus 1 because otherwise you can compute the exact matching. There's no point to get approximation accuracy. So the total space is within semi-streaming and polylog n. Now we only need to prove the correctness of the algorithm. So for each bidder, we define the item variation. I mean, if for each bidder has a uniform variation of 1, the utility of a bidder is 1 minus the price of the item he owns, or if he doesn't own anything, we define his utility to be 0, naturally. We define a bidder I to be epsilon happy if matching I to any item in its neighbors does not increase its utility by more than epsilon. This is actually not an intuitive definition, but we will use it frequently. So a simple observation is that, well, at the end of each round, the matched bidders and the bidders with an empty demand set must be epsilon happy. Because if a bidder is matched, the matched item should have minimal price before updating its prices. So since it's a minimal price item and you increase the prices by at most epsilon, it must be epsilon happy. Because matching it to another minimal item prices, that item should be has price at least this matched item minus epsilon. And or if this bidder has an empty demand set, then it means that every item in its demand set has price 1, which means the utility must be 0 and it must be happy. So we will let OPT be the set of bidders in the optimal matching. And we claim that up at the end of the algorithm, at least the 1 minus epsilon fraction of the bidders in the OPT set be epsilon happy. And yeah, we will use, this can be proved by using the following 2 partition functions. The argument is super easy, but I guess I don't have time to go over it. So yeah, this proof, the paper is like, the technical part is like 1 or 2 pages, is in SOSA. So anyone interested can look at it. It's basically the same as I write here, but what I wrote is just the same, I guess. Maybe not, I type it differently, but the idea is the same. So we have go over a simple approximate streaming algorithm. The last piece is like, I will briefly introduce the exact matching algorithm. It works for maximum weighted matching, and it requires square root n passes. It's an exact algorithm, so it's not approximate. So previous semi-streaming algorithm either requires n log n passes or are only able to find the approximate solution, like our previous algorithm. So there are some ideas going on here. Like in the Fox 19 paper, there is a semi-streaming algorithm. They provide a parallel algorithm, but we have a semi-streaming version. That is for reachability. Reachability is just in the directed graph, you want to find ST is reachable from S to T, where is reachable. So this algorithm can be transformed to finding one augmenting passes in like n to the 0.5 plus the small o1 passes. So if you want to use their augmenting pass algorithm to find a small o(n) pass algorithm for matching, then you basically need a small o(n) pass algorithm to find the matching of size at least OPT minus some n to the 0.5 minus omega 1. Because, well, if you have this algorithm of small o(n) passes, you can just augment this matching one by one using the reachability algorithm. I mean, if your goal is to obtain a small o(n) pass algorithm. But there's no existing algorithm can do this because the current best trade-off is giving, actually it's our algorithm I talk about. And we don't have a better trade-off algorithm. If it has, then it only works for very large epsilon. But here we need epsilon to be like n to the 1 over n to the 0.5 approximately. So it doesn't work, this idea. So this is just what we have before. That is, like I said, we don't have a good trade-off here. The best trade-off here, 1 over epsilon, but it does not work for epsilon if it is very small inverse polynomial. So, so I will go over just the high-level ideas of this algorithm. We have 4 steps. The first step is to solve the maximal, to solve the maximal weight bipartite matching we consider is dual, the generalized minimal vertex cover problem in bipartite graph. Then you approximately solve MVC using interior point method. But unlike matching, why we solve the MPC instead of the matching itself is because the number of LP variables in MVC is just n, which can be stored. But the number of LP variables in matching, because you have m edges, then you have m variables, which you cannot apply LP because you cannot store it in semi-streaming. The third step is you compute the optimal dual solution from the near optimal solution to MVC, because IPM gives a near optimal solution. You need to do some rounding, but the rounding might not be unique, so you need isolation lemma. And the last step is transform the dual solution to a prime solution in limited space, because you only have n polylog n. So here we need alternative construction. It uses a generalized isolation lemma. So this is just the high-level ideas, and it's the details of what I said. So, well, actually there are some technical stuffs going on here, but I cannot go into details here because I don't have time. And yeah, so let's do a recap. So for this exact algorithm, it's the 4 steps are, first of all, you approximately solve the dual MVC using IPM. You need to perturb the vertex weight to give uniqueness. And this step 1 can be done in n polylog n space and square root n passes. Then you compute the optimal dual solution from the near optimal solution. And this rounding can be done in constant passes. It's not constant, polylog n passes. Then you transform the dual solution to a prime solution in limited space, n polylog n space. And to do so, you need to perturb the age weight, and you use step 2 again to find at least m times n-tight inequality constraint and in limited space and passes. Then you just record the current best maximum matching, and you can repeat this. So as a summary of the talk, well, we give motivations of sublinear time algorithm for graph problems, and the models are MPC, PRAM, and semi-streaming. And we consider 2 problems. The first problem is parallel connectivity algorithms. The first result is a simple algorithm with log n running time. The second is a log diameter running time in the arbitrary CRCW PRAM, which is the first. And then we consider the matching problem, mostly bipartite matching in the streaming model. The first result is approximate algorithm and has a state-of-the-art trade-off, but it only works for cardinality matching. Then we have an exact algorithm which works for maximal weight matching. All the previous streaming algorithm either only found the approximate solution or it requires n-log n passes. We break this barrier. We use square root n passes. So the byproduct is square root n passes algorithms for more minimal vertex cover. And you also has a near polylog n passes SDDM solver. This is symmetric diagonally dominated matrix solver. Yeah, I think that's all. And thank you.
Yeah, thank you. Yeah, these are very interesting results.
Okay.
So I have to go in 1 minute because I have a PC meeting.
Yeah, sure.
Yes. So, but you guys can stay around and ask questions if you want. Okay,
Yeah,
bye.
The talk ends at 5:30, right?
Yeah, but no worries. So if anyone has question, we can ask questions. Otherwise, we can stop the talk. Okay, so if there's no question, I guess, yeah, this is it. Thank you, Cliff.
Yeah.
This is a cool result.
Yeah, okay, thank you. Thank you for your attention. Happy to share more with you after I get to CMU next semester.
Sure. Yeah, looking forward to seeing you in CMU.